Let's start another class of autonomous systems. Do you remember last week what we were seeing in autonomous systems was how to build road maps, okay? We say that road maps are graphs that contain to each node, to each vertex position, a configuration for our robot, and the edges are valid paths. It means that the robot can traverse from one edge, from one vertex to another vertex through this edge in a safe way. Okay, there are no obstacles in the middle. All the configurations are available, etc. Possible, etc. However, we don't learn how to find the best path from one specific node to another. We just learn how to build the graph, not how to find paths inside this graph. Okay? Then today is exactly what we are going to learn. Several algorithms that will help us to search paths or the most optimal path inside a given graph. Then let's start. Some introduction. You already see this slide last week, okay? This is how we define a graph. A graph is a set of vertices. As you remember, for us, a vertex is a valid configuration for a robot, and a set of edges that basically connect two different vertices, two different configurations. The only thing is that for us, we will assume that all these edges belong to free space, okay, to C-free. Graphs have several characteristics. We already talked about that. They can be cyclic, acyclic, directed, undirected. We can find multiple paths. This is something that we will see today, that to reach the same, starting from the same vertex and reaching the same vertex, the same goal vertex, we can find multiple paths, and the idea is to discover which one is the best one. And sometimes we use it to represent networks. The other day I mentioned that, but I do not show you any particular slide about that, is that there is a specific group of graphs that are called trees, and trees are a little bit special because they have this hierarchical structure. Basically, in the trees we always have a root tree, okay, here have this root tree, and then each node, for instance, this vertex here, this node here, it has one parent, that is this one, and has two childs, this child and this child. Okay, this is a little bit special because with edges, with graphs, we don't talk about parents and childs. We always talk about neighbors. We all have there is this. We lost this sense of hierarchical structure. All the algorithms I want to show you today can work for both trees and graphs, okay? Then what we are going to do, then given a graph, given from this graph an initial vertex and a final vertex, imagine this is the initial one, this is the final one, or this is the initial one and this is the final one, we are going to find a path moving only through the edges that are already defined in this graph that found the root that, according to some cost that we can specify, is the most optimal one. And to do that, we have two big families of algorithms. The ones that are uninformed. Uninformed means that they only rely on, they know the configuration, they know the graph, they know how the edges how the edges connect all the different vertices, all the different configurations. The maximum thing that we can assume here in the uninformed search is that I can know the cost of moving from this vertex to the neighbor vertex. I mean, if I'm here and I can move there, there, or there, these are the three edges that belong to me and also to these three other configurations, then I can know this cost. We will see that in some of these algorithms, this cost will be, this cost will be 1. This cost will be 1. For some other, no, this cost will have a specific value, n. What happens today? Normally, the cost is always positive because we assume costs are positive. And for some will be 1, for some will be n. It's different from each neighbor, but we will assume that this cost is always positive. This is for uninformed search. When we move to the informed search, for uninformed search, we basically will see these three algorithms that you have here. That is the breadth first search, the depth first search, and the Dijkstra algorithm. Super classical algorithms, and mostly several of you or some of you already know. And then when we move to informed search, we will use something that is called heuristic. Heuristic is a function, now I will explain it a little bit, but basically it's a function that estimates the cost to the goal, given a particular an estimation of how far or how costly is to reach the goal from this particular vertex. And then using this heuristic, this extra information, this privileged information, we will guide the search in a more efficient way. The idea is that informed search algorithms are more efficient than uninformed search algorithms. However, we not always have these heuristics. Okay? Not always we can have access to some function that estimates the cost to the goal. And some of the algorithms that we will see here are the greedy best first search and the A-star algorithm. We will not enter in the D-star algorithm. It's a little bit more difficult to implement, and it's not in the labs. In the labs, we will only ask you for these ones. Then let's take a little bit of attention to what an heuristic function is. The definition, I already give it to you. An heuristic function, we normally use the letter h to describe an heuristic function, and it's h of n, where n is a node or a vertex in the graph. Then it's the function that estimates the cost from the node n, or from the vertex n or v, whatever, to the goal. Then we need to know where we go. You remember, every time that I present a new algorithm, I always tell you, to use this algorithm, you need to know at least from where you start and where you go. And then additionally, I don't know, the orientation to the goal, back algorithms, or the distance to the goal, or some other back algorithms, or the graph that connects the current node to the goal, some extra information. When we use heuristics, of course, we need to know the goal because the heuristics depend on the goal. Then we need to know where we start, we need to know the full graph that contains the roadmap in which we can move. We need to know where is the goal, and we need to know the heuristic function for all possible vertices. Then, given any vertex in this graph, which is the estimated cost to reach the goal. And heuristics have two very important properties that you have to understand and to be sure that when you use an heuristic, the heuristic, or when you build an heuristic, when you program an heuristic, that your heuristic, at least the first one, it's always there. That is that heuristic is admissible. The word admissible here means that it never overestimates the true cost. It means, imagine that we have a graph here. Let's draw a very simple graph. Something like that. I don't know. Okay, this can be a graph. Then, if the only way for this node to reach this, well, the only way, no, if there are two solutions to reach this one is this solution and this solution, then the heuristic, if this is the goal, the heuristic for this node here has to be equal or smaller than the minimum path. Okay, equal or smaller than the minimum path. Normally, when we use 2D or even 3D, doesn't matter, but there is one function that is very easy to compute that is always equal or smaller than the reality, that is the Euclidean distance. Okay, for us, for reach any of these nodes, if we use the Euclidean distance, in the worst case scenario, well, in the worst case scenario, imagine if I compute the heuristic from this node to the goal, this is the direct path, then the real cost is the Euclidean distance. If the heuristic is the Euclidean distance, then the heuristic will be equal to the reality. It's admissible. In this case here, that is not exactly the Euclidean distance. The best path, I don't know if the one that goes below or the one that goes on top, probably is this one, the best one. This is a little bit more than the Euclidean distance. Then the Euclidean distance will be still smaller. Then again, it's an admissible heuristic. Of course, when you start to increasing the dimensionality of your robot to using not only position x, y, but using orientations, it's not so simple sometimes to find a nice heuristic that still represents correctly the heuristic, but is admissible, is still admissible. Of course, imagine you can put an heuristic of 0, it's always admissible, but it's not informative at all. Then it's not helping us to find which is the best way to proceed while inspecting this graph. This is a very important property, the admissibility of an heuristic. The second one is not so hard, let's say, it's the consistency. And consistency is formally described with this equation here. Basically, what this equation here is saying is that the heuristics for the node n must be equal or smaller than the heuristic for the node n'. Imagine that n' is a neighbor of n, plus the cost between these two. This way, the heuristic will always be reducing and reducing and reducing and reducing, okay? When you are far from the goal, the heuristic will be bigger, and the moment that you are getting close to the goal, it will get been reducing, 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 because this heuristic has to be at least this minus the real distance, okay? If we use the Euclidean distance, this works. If you create your own heuristic because your state, the way in which you define each vertex, each node in the graph, contains some other dimensions that are not as simple as an XY position, then you have to be careful that this is true. For some algorithms like the A star, it's super important that the heuristic is admissible. If the heuristic is not admissible, you cannot ensure that you find the optimal path. You can be finding a path that is not the optimal one. However, if in addition of the admissibility property, your heuristic is also consistent, not only you will find the optimal path, but the way in which you find it will be the optimal way. There is no better way, let's say, to find it. Then, after this brief introduction about what is graph search and what are informed and uninformed algorithms, let's now go to see the real algorithms. Let's start by the uninformed algorithms. And the first one that we will talk about is the breadth first search. The breadth first search algorithm, I have here, if you go to the wiki, there is this, is the same graphic that I have here, but with an animation. Basically what we have here is, we start, here it's a tree, but later I will show you that the same algorithm can be applied to a graph, okay? It's just with a tree, it's much simple to see, and I think it's nice, at least the first time, to see it with a tree. We start with inspecting node A. Here the idea is that we start at node 8, and we don't know where is the goal. Maybe goal is C, is G, is H, we don't know it. Then the sooner that we find the goal, we stop. Okay, here they assume that the goal probably is at node H, then they explore till the end. Also, there is people that you can use this algorithm just to build the path from all possible nodes to the original node, okay, to A. Then we will see the algorithm. But the idea is that the breadth first search is like if you do breadths in a piece of bread, okay? It starts for the first one, it just cuts here, then, yeah, I cannot draw that. Then you analyze all the childs in this case, or all the neighbors of node A, that are B and C. Then once you have analyzed B and C, you analyze all the childs or neighbors of nodes B and C, that are all these four. And when you have analyzed these four neighbors, you analyze all the neighbors of nodes D, C, F, G. Basically, it's only H. If we look to the complexity of this algorithm, it tells us that the complexity is the number of vertices plus the number of edges. It means we need to check everything in order to use it. And this algorithm can be used when we assume that the wage, the cost from reaching from A to B, or the cost from reaching A to C, it's always the cost between one node and its neighbor. It's always, it's always one. Sorry, I thought I was printing. Okay, it means that we assume here that is, or we call that the graph is unwedged, that there have no wedge in the edges, or that the wedge is equal for all of them, that is exactly the same. Okay, let's go to see the algorithm, how the algorithm, okay, here there is more or less an explanation of the algorithm just in words, but I prefer to use it, the pseudocode version. The idea is they tell us how the roadmap looks like. The roadmap is the graph DE, is this graph. And they tell us also where the vertex starts. Of course, if they don't tell us where the goal is, what we will end up doing is generating a kind of policy. You know what a policy is? A policy that for each node n, they will tell us which is the parent of this node, which is the parent of this node, which is the parent of this node. And if we follow this policy for any possible node, okay, for any of these nodes here in this graph or in this tree or whatever, we will reach the starting node. Of course, if in addition of the starting vertex S, they tell us the goal G, then we can stop building this policy the moment in which we reach the node, the goal node. And then we only need to follow P of G, it will bring to some vertex, this vertex, P of this vertex, P of this vertex, until we reach the starting node. Okay? This is the idea. Okay, then, whenever we have this information, the graph, the starting node, and optionally the goal node, we initialize all the vertices B, as unvisited, except for the starting node that we call that it's visited. You can add a flag, you can put it in a special list of visited and unvisited. This is up to you. And then what is important is that we initialize this Q. This Q here, it has to be a Q, and then later we will see why it has to be a Q. And we put S in this Q. Basically, the way that Qs work is that you put things at the beginning and you remove things from the last. It's a FIFO. First in, first in, first out. The first thing that you put inside this queue is the first thing that you remove. If you put 3 elements in this queue, then you will first remove the first element, then the second element, then the third element. It's basically, if we draw it, is you put things from here and you remove things from here. Okay, then we remove from this queue whatever element is here, while there are elements in this queue. At the beginning, it will be only the vector, the vertex S, and then for each neighbor of whatever we have removed from this queue, that is from each neighbor B of U, what we do is put B as unvisited. Well, sorry, if B is unvisited, then remember, initially everything was unvisited, then we mark it as visited, and we say that the parent of B is U. What means the parent? This is the policy function. It means that if we need to reach the starting here, instead of building the path from the starting to the goal, we will always build the path from the goal to the start. And to do it, we will just check this policy or P function, okay? We will go to the goal, P of goal, and we will say, okay, which is your father? This one. And then we will go to this other vertex and we'll say, which is your father? This other. And etc. till we reach a node that is the starting node, that is the S node. Okay? Then we will mark B as visited, this neighbor as visited. We will say that to reach this vertex B, we have to do it from the vertex U, and then we will put B in the queue. And that's all. And we are doing that forever and ever. Okay? And just doing that, we apply the breadth first search algorithm. As I told you, in the other example, there was a tree, and in a tree is very simple. Here is not so simple because it's a graph, but it's super short, then it will be also very simple. But we can try to do that, okay? Initially, all the vertices, let's assume that this is the S vertex, okay, where we start, and assume that here we don't have a specific goal. We just want to create this P function for all possible vertex. Given any vertex, I want to know the route it has to follow to reach S. Okay, if I don't give you a goal, this is the output of the BFS algorithm. And then initially all the vertices are unvisited except this one, and in Q I only have 0, okay, the vertex 0. Then the first thing I have to do, according to the algorithm, is while Q is not empty because there is this 0 node, is remove whatever from Q. Then U, I remove that. Now my U is equal to the N0 if you want, N0, node 0. And then for each neighbor of B, I have to check if this neighbor is unvisited, mark it as visited, tell that its parent is U, and put it in Q. Which are the neighbors of S? The neighbors of S are of node Z, node S, that is the node 0, are the node 1 and the node 3. Then always I will put here or numbers or letters for the exercises. Now I mean, try to follow, if I put 1 and 3, start for 1. I know both are neighbors of 0. Then the algorithm could pick up 1 or could pick up 3. But please, I just ask you that always use the same order that I give you here. Then if we pick up that this is the first neighbor of 0, we check if it's unvisited. Yes, it is unvisited. It has no this kind of cross I put in the other. Then the first thing is we say this is visited. Then we have here, okay, P of 0 will be null. The 0 has no father. P of 1 will be 0, okay, because the node U is 0, 1, 0, whatever. We will indicate that this is visited, and then we have removed 0 from Q, but now we have add U from Q. And then we continue, because we have to do that for all the neighbors. Then we go to the node 3, it's already unvisited, then we mark it as visited. Then we say that P of 3 is again 0, and we add 3 here in the queue. Okay, I think it's done, no? This is we haven't queued. Okay, then we go again to the beginning of the algorithm. The beginning of the algorithm, we check if Q is empty. No, Q has 2 elements, 1 and 3. Then we remove the first element. We remove the element 1. Then I remove 1. And for all the neighbors of 1 that are 2 and 3, I have to check, are they visited? Okay, let's start for 2. 2 is not visited, then I mark it as visited. I say that to reach 2, I have to pass through 1, because now I'm analyzing node 1. And I add 2 in this queue list. And the second neighbor, it's, well, the first neighbor was 0, that was already visited. The second neighbor was 2, that was unvisited. And the third neighbor is 3, that it's visited. Then I have to do nothing if it's already visited. Okay, then let's continue. Now I have to continue with 3. Okay, then I remove 3 from my queue. 3 has 3 neighbors, 0 that is visited, 1 that is visited, and 4 that is not visited. Then I add 4. Okay, first I say that to reach 4, I have to do it from 3. I add 4 here, and I mark it as visited. And that's all. And then I continue. I remove 2 from my queue list. All the neighbors or Q are visited. Then I do nothing. I remove 4 from my queue list. Let me remove that. I remove 4 from my queue list. All the neighbors or 4 are already visited. Then my queue list is empty. Then I'm done. And this is the output of the BFS. Okay? It's basically, if I have to reach 4 from, if I want to go to 0 from 4, then P of 4 is 3. I have to move this way. Then I go P of 3 is 0. I go this way. If I have to move from 2, then P of 2 is 1. And P of 1 is 0. Is this the best path? Okay, as we told that yeah, it is, no? Because if we pass through here, then it's cost 1, 2, 3. If we move from 4 to 0, passing through 2, if we do this path, it's cost 3. However, if we pass through here, it's cost 2. From 2, again, if we pass from here, it's cost 3. If we pass from here, it's cost 3. If we just follow this, it's cost 2. Then what we can say is, what it was explained here, that if the paths are unweighted, that is the case that all of them has weight 1, BFS finds the shortest path from the start to any of all the reachable vertices, okay? Of course, as this is a graph, maybe, I don't know, here we have node 5 that is not connected, then we cannot connect 5 with 0 because it's not connected, okay? But this is the most simple algorithm, BFS, but it's okay. If the graph that you have is unweighted, you can use it. Yeah, please.
If the 2 were the goal, then I'll continue to visit 4 or I'll stop the...
No. Yeah, I don't know if this is marked here at some place. This is no, I thought it was here. Probably is in a future slide. No, if you are not interested in obtaining all these P function, and you are only interested, for instance, on reaching node 2, the moment in which you know that for reaching node 2 you have to go from 1, you can stop here. You don't have to continue exploring. And then you avoid to exploring the whole node, okay? The whole graph, sorry, all the nodes in the graph. Yeah, this is good to say it, that you don't have to analyze the full graph. The other algorithm that is super similar of this one is the depth first search. Again, I don't know if here there is also an animation at some place. Yeah, here it is. Depth first search is slightly different than the breadth first search because instead of doing like breadth of a piece of bread, what it does is starting for the first child or the first neighbor, depending if you are using trees or graphs, of the starting node, it goes to the maximum depth possible. And then when it reaches the maximum depth possible, then it just goes for it tries to backpropagate that. In this case, no other nodes have childs, then it has to reach again node 1 to find a second child. In the second part, you see 5, 6, 7, then it backpropagates to node 5, and then it explores node 8, and then when it has done node 8, it backpropagates to node 1, and then explores node 9 and 10. Although the result seems pretty different, as you can see, time complexity is exactly the same. The algorithm is almost the same, and then there are some advantages and disadvantages. The main advantage is that it uses less memory. In the breadth first search, this queue that I show you, that in our experiment was super sure that contains 2 or 3 nodes, in a real example can contain millions of nodes, okay? However, if you use the breadth first search, this used to be much smaller. However, here we don't ensure that even if the graph is unweighted, that we are going to find the optimal path. Maybe to reach, okay, in this case it's a tree, and probably we will have the optimal one, but maybe to reach a specific node, the first time that we reach this node, just going the maximum depth, it's not the most optimal one. If we move to the algorithm, the nice thing of the algorithm is that it is exactly the same that the breadth first search. You can spot the only difference, and the only difference is this one. Stack. Instead of a queue, we use a stack. For the rest, it's exactly the same. What is a stack with respect to a queue? Stacks, you have to imagine that are like that. I put here one node, node 1, I put here another node, node 2, I put here another node, node 3. The moment I have to remove something, I've been putting this, I start removing node 3. Then I remove the last one I have input. Okay, yes, LIFO, no? Last in, first out, instead of FIFO. For the rest, it's exactly the same. I use exactly the same pseudocode, okay? I use the pseudocode for the breadth first search. Here, we use a queue. And for the depth first search, that here we use a stack, okay? This S-push, this is a stack. This is how I like to implement this algorithm, and it's exactly the same algorithm, just changing this structure. However, what I realized while doing the class was that here in the video that we see here, this implementation, this is not using the stack. This is using a different algorithm to implement the depth first search. It's exactly the depth first search, it's the same, but look here that the branch that is explored first is the one in the left. While if we try to do the same, I try to put that in the slides now. If we, well, no, not this one, sorry. If we try to do the same here, this is the same schema. If we try to do that using the stack, okay, we will stack first the A, then the moment that we remove the A, it's because we are analyzing A, then this is the first node that we analyze. We put all the childs of A, then B, C, and D. The first one that we remove is D. Then this is number 2. Then we put all the childs of D, that is J. Then we remove J. This is number 3. J have no childs. Then we remove C. Then is number 4. Put all the childs of C, that is F and J. Then we remove, this has to be larger, this is stack. We remove J. This is number 5. J has no childs. Then we remove F. F is 6. We add H here. Then we remove H. H is 7. Then we remove B. B is 8. We put E, that is the child of E. At the moment that we remove E, this is 9. Then we add the child of E, that is I. And we remove this, that is 10, and that's all. This is exactly the opposite. You see, the first branch that we analyze is the right branch, not the left one. You see this difference here. This is, both are depth first search algorithms, okay? Just one starts for the right and the other starts for the left, but the algorithm is the same. Both are correct versions of depth first search. However, I prefer to add here just an extra slide explaining the algorithm that they are using in the wiki, that is probably a more popular version of the depth first algorithm that uses recursivity. Okay, I don't know how well are you about recursivity, if you know if you have ever programmed something using recursivity. Normally when we program something using recursivity, for one side we have the main algorithm, and then we have a function. In this case, the function is DFS. And this function, inside this function, DFS, we call the function itself. Okay, then it's super important when you do recursivity that here it has to be always 2 branches. In this case, we have this if. If we have unvisited neighbors of the node U, we call the recursivity part. If we don't have, it should be this else. We do nothing, we just return, okay? It's super important when you do recursivity, always to have these 2 branches, and also never call the same function with the same input. I mean, I need to modify the input, otherwise I just will create an infinite loop, okay? If you apply this recursive algorithm instead of the queue-based algorithm that I show you here, sorry, the stack-based algorithm that I show you here, what you will obtain is that we first start in A, then for all the childs of A, then we go to the first one, that is B, and in B, for all the childs of B, we call the algorithm recursivity, then we go to E, then for all the childs of E, we call the algorithm recursivity, then we go for I, because I has no childs, we return, because E has no more childs, we return, because B has no more childs, we return, and then we continue for the second child of A, that is C, now B is 5. And then we call for all the childs of C, this is 6, for all childs of F, then this is 7, this has no more childs, this has no more childs, then let's go here, yeah, this has another child, and this is 8, then we go, no more childs, here there is one more child, that is D, and then from here it has only one child, and it is 10. And now it's exactly what you have seen in the Wikipedia. The problem of doing it with recursivity is that when you have graphs instead of trees, it's not so easy to remember where are you, which is your context, okay? In Python, it do a very nice job of keeping the context. Here, you have to keep the context by yourself. This is why I prefer, or I I think it's better for you to implement the LIFO stack. With the LIFO, it's very simple. You just need to draw your stack and start putting things in this stack and removing things from this stack. And that's all. This is super simple, and you will not fail in case that instead of a simple tree, that for tree is trivial, you have something more complex, like a graph. Okay, this graph is, again, super simple, but it will be easier for you. Both algorithms are exactly the same. One uses a FIFO and the other uses a LIFO. It's the only difference. Breadth first search used to be a little bit better because of that it finds the shortest path if we are using an unweighted graph, while the DFS do not guarantee that. However, it has more memory cost. Nowadays, this is not a big issue, but okay, late in the 50s, 60s, where these algorithms were invented, this was an issue. Yeah, basically is that. The only thing, or the main thing that changes is that. It's how we manage the data structure. Is the only thing that changes between one and the other. Okay, let's move now to another, yeah, we have enough time. Another uninformed algorithm that I think this is the important one, the one that you have to learn, if you don't know it already. That is the Dijkstra algorithm. Dijkstra algorithm probably is the oldest algorithm you will see in this course and maybe in the whole master. It's a super old algorithm, but it's a really useful algorithm and it's being used nowadays. The idea here is that it's able to find the shortest path from a starting position to any other node, any other vertex in the graph, any other. And here we don't have to have edges that are unweighted. I mean that all the edges have the same weight, that it is very unrealistic. We can have edges with different weights. The only thing that we cannot have is negative edges. Okay, this, if we are using distances, for sure we will never have negative distances, but imagine that instead of distances we are using energy, the energy for moving to one node to another node. If we are using an electric car that when there is a slope down, it recharges its batteries, it may happen. Okay, it's a very particular case, but it may happen, or a drone that when it moves from one point that was on the top to another point that is on the bottom. It just not only not uses energy, but the potential energy, it's a little bit higher, and then it can do a free extra trajectory or movement or whatever. Then in some particular cases, we can have negative edges, but it's not the normal, okay? Normally, if we, for most of the codes that we will define, the cost will be always, or at least zero or positive. The good thing of the Dijkstra algorithm is that it's uninformed, then it do not rely on any heuristic function. And it means that it's one thing less that we have to think about. We don't have to think on any heuristic function and be sure that it's admissible and all this stuff. And it uses a queue, but it's not a standard queue like the one that we have seen in the breadth first search. It's a priority queue. It means that we will put all the elements, all the nodes in this queue, but we will not remove or the first one that we have input or the last one, like in breadth first search or in the last input first output and DFS, but the one that has one value that is the smaller one. Now we will see. This is the paper. It's just nice to see it because it's super old. This is the algorithm in words. I try to put it here in words. How we initialize. Of course, we need a graph that contains the roadmap in which we are going to plan. Then we need the starting node. We don't need the goal node because we are going, again, if we have the goal node, the moment in which we reach to the goal node and that in which we select the goal node, we can finalize here and we already have the path to reach this node. But the idea of Dijkstra is that you can apply it to the whole graph and then you have this graph pre-computed, and the moment that you have to go to a different position, you don't have to do anything else. You already have it you have already computed. The problem is that the Dijkstra output changes if you change the starting position. Then, if you want to pre-compute all the paths in a route map, you need to apply Dijkstra starting from all different vertices. okay? You have to do it this way. Then we have the initial node, that is the source. We have the distant function. The distant function tell us how far or how costly is to reach this node from the original node. Then the distant function at node S will be 0. You have it here. And in the beginning, the distant function for any other node will be just plus infinity. Okay, we don't know it. And again, what we will compute is this P function, this policy that will tell us from each particular node which is the parent, to which direction we have to go. We start adding all the nodes, all of them, into this MIME priority queue, called Q, and it's keyed, what I told you. Here we are not going to take the first one or the last one that we have introduced, but we are going to take the one that has this distance, is smaller. Of course, at the beginning, all the nodes have this distance, infinity, except for the starting node that have it to 0. Then the first one that we will remove is the starting one. Okay, then we extract one node from Q. The first one, this will be the node 0, the node S, sorry, the starting node. But in general, will be the one that this distance is minimum. And we will set this as the current node. Okay, this will be our current node. Remember, here it's pretty similar of what we were doing here. We also remove one, and we assume that this is the current node U, and then from this node, we visit all the neighbors. This is more or less what we are going to do here. For the current node U, we get all its neighbors that are still in Q. That are still in Q is the same way to say that are unvisited as before, okay? However, here, as we need this prioritized queue, we can use Q just to indicate two things, which is the one to remove the one that has a smaller distance and to indicate which one have been visited and which one have not been visited yet. If they are in Q, they are unvisited. If we have removed it from Q, remember here we have extracted S, then S is not anymore in Q, S is already visited, but all the rest will be still unvisited. Then for all the neighbors B of U, okay, U is the current node that we are checking at, all the neighbors, all the vertices that are connected with an edge with U are the neighbors, then all the neighbors B, what we do is to compute this distance. And this is like a candidate distance, no? This is the cost to reach the neighbor B will be the cost of reaching the neighbor U, that you should know this cost at this moment, plus the wage of the edge between U and C. Sometimes I put W, sometimes I put just C, okay? The cost between U and B. Sorry. Okay? I try to make the algorithm all very similar, but I always miss something. Then, if this cost that we have computed here is smaller than the actual cost, the current cost of reaching node B, okay, of reaching the node of this neighbor, if what we have computed now is smaller than reaching this neighbor, then we just update two things. Update the cost of reaching neighbor B, but we also update, we are going to reach neighbor B from U. Okay, we are just updating. Remember that B is a node that is inside Q, and we can access to its memory, change whatever parameters, and if we don't remove it from Q, it's inside. And then when we have done that, we repeat from 2. It means we have extracted one node from Q, initially was S, but the second time we will extract the second node, probably one of the neighbors of S, that because of that, it has, because of this function here, no? Its distance have reduced from infinity to distance of S that was 0, plus the cost of reaching, okay, here, if I change here the W, here I should change it to, plus this code, and we're just doing that. And we do that until, or we have found, we have completed all the graph. It means that there are no more nodes in Q, or just we have reached we have removed it from Q, not the moment that we it can be, some people here it confuses. Imagine that one of the neighbors of you is goal. Okay, and then we just discovered that we can reach goal in a more or less cost, because goal initially the distance to goal was infinity, then the distance of goal, now it's the distance from some neighbor of the goal plus the cost between one and the other. And we have updated this and we say, okay, I know how to reach goal. No, in this moment you cannot stop your algorithm here. You have to continue till you extract the node that you extract from Q. It means the node that has the smaller d in Q is the goal node. Okay, in this moment you can stop. If you don't want to compute the whole graph, if you only want to compute the minimum distance between the starting node and the goal node. But not in the moment in which you update the value of goal, because maybe later you will find another node that reaching goal from this other node is shorter. Then until you don't extract the node goal from Q, you cannot stop applying Dijkstra algorithm. This is the algorithm. It's, I think, one line more or two lines more than the other, but it's almost the same. We initialize D to infinity and P to null for all the vertices, except, okay, again, here you can put, well, no, for the node S, the distance is not infinity, is 0, but the P is null because it's the starting node and it has no parent. You can, whenever you reach P, you are done. You have finalized the path. Then we initialize the priority queue and insert all the nodes in this priority queue. And then we are extracting always the node with a smaller b, and for all the neighbors, we should just do that. We first compute this tentative cost. Normally we call that a tentative cost. And if this tentative cost is smaller than the real cost of, or the current, not the real, of the current cost, then we update the current cost with the tentative cost, and we also update the function pi. That's all. Let's try, okay, this is an example, a little bit bigger than the one that we will do now all together. Initially, the cost of reaching all the vertices, here is the initial node, okay, I don't know if you see it, it's here. The cost of reaching all the initial, all the vertices is infinite, but then the moment in which we start exploring, then we update the cost of these algorithms until here we have updated the cost of absolutely all the vertices in the graph. Okay, then if instead of, now I assume I plotted just this in green because I assume that this was my final goal. But if I want to reach from here, let me just try to draw it here, maybe it will be easier. From here, then I don't have enough information here, but probably the P function will tell me that from here I have to move to here, then from here I have to move to here, and then from here I have to move from here. All this information will be codified in the P function, and the only thing I plotted here in this drawing is the total cost of reaching this node from the starting node that was here. Okay, then let's try to do a very simple example with applying the Dijkstra algorithm. For the Dijkstra algorithm, I used to create like a kind of table in which I say the ID of the node, the cost, the distance, sorry, the distance to reaching this node. Okay, if it's visited or unvisited, normally it's just pushed on a star on top of it, and the pi. Okay, from where I'm reaching this node. Okay, initially all the nodes are unvisited. For visited, unvisited, I will just put it with a star. Then the first node here, assuming it's 0, then the cost of reaching 0, the node 0 is 0 again, and then this is null, has no parent, the node 0. Then from here, what I have to do, if I follow the algorithm, is take from the priority queue, extract the u that is minimum, the distance is minimum from the queue. Then if all the elements, here I could put 1, 2, 3, 4, no? I can put, sorry, it's not drawing. 1, 2, 3, and 4, no? And all will be infinite, 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 and all will be null, 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 and null. Okay, then which one is the smaller one? Okay, this is the smaller one. Then for the smaller one, I need to check if reaching 1 and reaching 2, that are these two neighbors, is cheaper from 0 or from its current parent. Reaching 1 will be the cost of reaching 0, that is 0, plus 3, that 3 is the cost between 0 and 1. Then the cost of reaching 1 should be 3. 3 is smaller than D. Then I update this. I update this with 3. And I also update this with P0. And then I do the same for 2. Reaching 2, it's the cost of reaching 0, that is 0, plus 1, that is this number here. Then here I will have 1. And again, I replace that by P0. Okay, I will just put 0 here. Now, I need to choose from the others, from the ones that are still in queue. Remember, I've removed that out of queue, then this is not anymore in queue. For the ones that are in queue, which is the one that has a smaller cost. The one that has a smaller cost is 2. Then from 2, I have to check all the neighbors. Okay, all the neighbors except for 0, that is not anymore in queue. But I have to check 1, I have to check 4, and I have to check 3. Let's check 1. The cost of reaching 1 from 2 is the cost of reaching 2, that is 1, plus 1. You see, there is 1 here. Then, because 1 plus 1 is 2, 2 is smaller than 3, then I just remove that, and okay, you can just cross it. Sometimes I prefer you just to cross it. Then I understand that you have changed it. And then, now here it's not anymore from 0, it will be from 2. Yeah, sure. Basically, what we used to have here, let me just try to, we have it like that. The cost of reaching node 1 from 0 was the cost of reaching 0, that was 0, because this is the starting node, plus 3, that is this connection here. Now, we are analyzing node 2. The cost of reaching node 1 from node 2 is the cost of reaching node 2, that is 1. We already have it here, plus the cost of moving from 1 to 2, from 2 to 1 in this case, sorry, from 2 to 1, that is 1 again. Then it's 2. 2, if you remember, this is this sentence. I'm talking about that, The cost of reaching 2 plus the cost of moving from 2 to 1. This is 2, and the cost or the distance of 1, that was 3. Because this is smaller, 2 is smaller than 3, I'm going to update D, and I'm going to update how to reach this node. It's clear? Good. Then here I just change that now this is 2. This is 2. And now I don't come from 0, I come from 1. Okay? I've checked this neighbor, but I have more neighbors to check. Not 0, because 0 it's already empty, it's not in the queue, but I have to check 3. The cost of reaching 3 will be the cost of reaching 2, that is 1, plus the cost between 2 and 3, that is 4. 1 plus 4, 5. 5 is smaller than infinity. Yes, of course it is. Then I can just put here 5. And it's not anymore null, it's P2. 2, sorry. And I have now the node 4. Reaching node 4, it's reaching node 1, not reaching node 2, sorry, that is 1, plus the distance between 2 and 4, that is 2. 1 plus 2 is 3. Then here I just put 3. And here I just put from P2. Okay. This is done. This is not, sorry, no, not this one. This one, it's not anymore in the queue. You don't have to cross it. I just cross it. If you just put some indicator, it's fine. I just cross it to make it more clear. Then we have now 3 more nodes in the queue. One has distance 2, one has distance 3, and one has distance 5. Because we always take the one that has the smaller distance. We take this one. This is node 1. Okay, then let's check node 1. Node 1 has 2 neighbors, 0 and 2. What happens is that both 0 and 2 are already out of queue. They are not in queue. Then I cannot update them. Then It's done. I don't have to do anything else. The next one is node 4. Node 4 has a distance 3, while node 3 has distance 5. Then let's go to node 4. Node 4 has 2 neighbors, 2 and 3. 2 is not in queue anymore, then I can do nothing, but 3 is in queue. Which is the weight or the distance to reach 4? The distance to reach 4 is 3, because it's telling me here, plus 3 plus 3, because this is 3, it will be 6. Because 6 is bigger than 5, I'm not going to update it. Then I'm fine. And now I have only node 3. Node 3, all the neighbors are already removed from queue. Then I'm done. Finally, what is my policy is that from node 1, sorry, this is not correct. This is a 2, eh? This is a 2, this is a 2, eh? To reach in node 1, I have to move to 2. For 2, I have to move directly to 0. From 3, I have to move to 2. And from 4, I also have to move from 2. This is the path that I have finally generated. It means that if I starting at 3, then I will move to 2 and then to 1, and the cost will be 5. And this is the shortest cost I have. If I start in 4, I will move from 4 to 2 and from 2 to 0. And then my cost will be 2 plus 1, 3. If I have in 1, if I start in 1, although 1 and 0 are directly connected, it's cheaper if I first go to 2, that is cost 1, and then I go to 0, that is cost 1, etc. This is the kind, all the information, sorry, I don't know, I try to do that, but if you do it a little bit larger and you just cross all the things that you are updating, normally, finally, there is a table that is very easy to understand, and then you just can draw the arrows according to the P function here, and everything is pretty clear. I don't know here with the tablet, I've not make it very, very nice. But this is the idea, okay? What you obtain, the P function, plus the distance, the final distance to reaching the goal, and how the algorithm works, okay? This is super toy examples, but I think you should be able to do that, not with 100 nodes, of course, but with 6, 7, 10 nodes maximum, okay? Of course, it's much larger, and we will have no time to do it here in class, but this is the kind of algorithms that I expect you to be able to do by hand. Let's continue. We have seen the uninformed graph search. We have presented 3 of the most popular algorithms to find things in a graph if we have no extra information. Now let's see a couple extra algorithms, the greedy best first search and the A** algorithm. Probably the A* algorithm, you already know it because it's super popular, that they use this heuristic, this extra information that can help us to find the best path in less time. As we have seen, using Dijkstra algorithm, we found the optimal path in the graph. The problem is that we have to explore almost all the graph in order to find it. With the A* algorithm, we can make this a little bit more efficient. Not always, but in some situations, yes. By the end of the class, I will show you some examples. Let's start by the greedy best first search. This is not a super popular algorithm, but I like this algorithm because if you combine the Dijkstra algorithm and this algorithm, A* appears naturally. Then, because I want to explain Dijkstra and A*, I also like to explain this just for completeness. Although it's not super useful or not the most popular algorithm at all. In fact, you can see that I've not found even the paper in which this algorithm was described, but it's very well described in this book. I don't know if you know this book. This book was very popular 15 years ago, something like that. I think that 2009 was the second edition or something like that, but in 2010, 2015 even, it was very popular because it just do summarization of all main artificial intelligence algorithms out there. And for artificial intelligence, it means graph search, okay? Algorithms that help a computer to do something autonomously, like finding a path in a roadmap. Right now, it has been very outdated because you know that there is a lot of new developments in the AI area, but it's still a good book. It's still a very good textbook for classical algorithms. And there are some of the things explained in this book that are super useful nowadays and that are very, very used in a lot of different domains. Well, let me explain. The Greedy best first search is, as I told you, an informed algorithm. It means that it uses an heuristics, and that this heuristics has to be at least admissible, and this is the minimum thing that we require to this heuristic. It's not guaranteed that the path that we found using the Greedy best first search is the shortest path. This is not guaranteed. Okay? But it's much easier to implement than A* and much faster. We need to compute less things, and therefore, for some situations, it can be good. As I told you, it's not super popular, but in some situations, it can be better than A*, at least faster than A*. A* is optimal, then better it's impossible in terms of the final path, the produced path, but it can be better in terms of it's faster to execute. The idea here is that we will have, instead of a single Q list or a single S stack, that like we have doing with all the uninformed search graph, here we have two lists, an open list and a closed list. In the closed list, we put the visited nodes, and in the open list, initially there is no node at all except for the starting node. Then again, here we need to know which is the starting node, and here is more normal that we have a goal, okay? Where we're going to reach. If we don't have a goal, if we have to analyze the full graph, probably better to use just Dijkstra. Then, while O is not empty, initially, as I told you, at least there is the starting node in node. What we have is we extract one node from this list, but again, this queue or this open list is a priorized queue. And here is not priorized by the distance or the cost to reach this node from the beginning, is priorized with the heuristic. It is the expected cost to reach the goal. Then we take the node that initially, according to the heuristic, is the one that will bring us faster to the goal. Of course, heuristics are an estimation, then maybe it will, maybe it not. Then we reconstruct the path. Well, if the node that we have taken is the goal, we are done. We just reconstruct the path and we return. Otherwise, we just move this node that we have extracted from the open list to the closed list, and for each neighbor B of this node U, if it's not in the open list and neither in the closed list, we set that to reach this neighbor, we have to do it from U. We update the policy, the P function, and we also insert the neighbor into the open list. And that's all. And we just repeat, okay? Here it's, instead of using words, using pseudocode, that for me it's always a little bit easy to see. Here, what is given is this heuristic function. For the heuristic function, we always indicate that. Okay, the heuristic function returns a value, and this value is a real that is greater than 0. Is 0 or greater than 0. Okay, the heuristic function returns a real number. It's that simple. We also need to know which is the starting node S, which is the goal node G. And what we initialize is, again, the policy null for all vertices. We have this mean priority queue. In this case, it's scaled by the heuristic function that we will call it open list, but open queue, you can say. And we also have this C list or closed list that initially is empty. What we do just at the beginning is to put the starting node to the open list. And while this open list is not empty, we extract one node that we will call it U, and this node will be the one with the minimum heuristic. The heuristic that tells us probably from this node is the closest that you can be to the goal. Then we extract this. If it's the goal, that's all. We just can reconstruct the path using pi from this node. Let's see which is the pi of this node, and go to another vertex, which is the pi of this vertex, and go to another vertex until we reach the goal, the starting node, sorry. Then, if it's not the goal node, what we do is just we have removed this node from O, and then we add it to C. And for each node of B, if they are not in the closed list, neither in the open list, we say that to reach node, this neighbor B, we have to do it from U, and we insert this vertex, this vertex neighbor, neighbor vertex into the open list. Here there is a very simple experiment of it. We can try to do it if you want. I think we start, here what it's indicated here in pink is the heuristic. Okay, what I don't have here, it's the real value, because I don't care about the real value. If you check here in the algorithm, we don't use the real value. The real value, I mean the real cost from moving from one node from node U to the vertex B. We are not using this information at all here. Okay, then it's another reason, if you only have the heuristic but you don't have this cost function, you can also use the greedy first search. Then this is the information that we need. Is just starting from this node. I think the goal was this one, because if you see the heuristic of reaching this goal is 0, it means the heuristic is the distance to the goal, or the estimated distance to the goal. And in order for the heuristic to be admissible, this distance has to be, this value has to be always equal or smaller than the real value. Then the cost of reaching the goal from the goal is 0, then the heuristic has to tell me 0. If here I have a 1, the heuristic is not admissible. Okay? And then what we are going to do here, we can create a similar table than in the Dijkstra, in which we have the ID, we have the heuristic, we know at which list the node is, and we have the h function, the pi function. Something like that. Okay, then we start with, I don't have numbers here. I thought I have updated these slides, putting values here, putting numbers, and I don't see it. No, okay. Maybe I just forget to upload it, sorry. I need to put some numbers, otherwise, then the number of the vertex, I mean, 3, 4, I don't know, 5, 6, and 7. Otherwise, I cannot just tell this is the ID 1 or ID 0 or whatever. Then, initially here we have only the 0 that is in the open list. The heuristic is 7.8. And this is null. I don't know, to reach the initial vertex, it has no, the pi function is not defined for the initial vertex. Then I extract from the O list the one that has a smaller heuristics. I have only one, then I just extract this one and I put it in the closed list. I remove this from the open list and put it in the closed list. And then for each neighbor, that is 1, 2, and 3, 1, 2, and 3, what I have to do is, if I remember well, is to put, if they are not in the open or neither the closed list, that is the case, I have to put here its heuristics. The heuristic from this one is 6, from the node 2 is 5.8, and for node 3 it's 5.0. And they are all in the open list. And I have to tell that to reach this one, I go from 0, and from 0. Let me just cross the zeros to differentiate it from the open list, okay? Maybe I don't know if it's clear or not, because then I will close the open list to put a closed list, but okay. Now what we have to do, take from the open list the one that has a smaller heuristic. If the first one was this one, now the next one is number 3, you see? Number 3 has the smaller heuristic, the heuristic is 5. Then I remove this from the open list and I put it in the closed list. And for each neighbor of 3 that is not already in the open list or the closed list, then 0 no, but 5 and 6 yes. 5 and 6 yes. I put here its heuristics. For 5 it's 7.6. For 6 is 5.0. 5.0. And these are all in the open list, and their parent is 3. Okay, that's all. It's pretty fast, this algorithm to execute. You see, I have to compute almost nothing. Again, in the open list, and the heuristic is 6 for 1, 5.8 for 2, 7.5 for 5, and 5.0 for 6. Then the smaller one is again 5.0. Then I take 5.0, I remove it from the open list, and I put it in the closed list. And for all neighbors of 6 that are not in the open list, neither in the closed list, the 3 is in the closed list, 5 is in the open list, I have only 7. I put here its heuristic, that is 0, and it's in the open list. And I reach this from node 6. I'm analyzing node 6, then the parent of 7 is 6. Okay, then I select again from the open list that I have 1, 2, 5, and 7, which is the one with a smaller heuristic, is 7. And because 7 is the goal, it's done for me. Then here, the path I'm generated is from 7, I go to 6. From 6, I go 7, go to 6. 6 goes to 3. And 3 goes to 0. Okay, this is just following pi. Then I have just to reverse the order, and then I go that from 0 I go to 3, from 3 I go to 6, and from 6 I go to 7. Is this the optimal path? It is not. Okay, the optimal path is going to 2, then going to 4, and then going to 7. What happens? Here the heuristic is not helping. This heuristic from here to here, the heuristic is well computed. I mean, the heuristic is the distance. I think if I do it correctly, when I compute these heuristics, I use the Euclidean distance. Then from here to here, it's 7.8 meters in the straight line. Okay, from this node to the goal, this is 7.8 meters, pixels, whatever. From here to here are 5.8. From here to here are just 5. Here are also 5. Here are 4.1. However, because I'm using a greedy algorithm, I'm not finding the correct solution. Okay, although the heuristic is okay, although I'm following the algorithm as it is supposed to, this algorithm is so greedy that it has been very fast to reach. I have not analyzed lots of nodes. I add them to the open, but if you check, I only have analyzed 3 nodes and I've reached the goal. It's quite fast. But in some situations, like in this special case that I've done this graph in this special shape, this roadmap has this special shape, the solution is not the optimal one. In plenty of situations, maybe I will not obtain the optimal one, but something close to the optimal one, if the heuristic is well computed. And because it's very fast, then it can be good. But it's not optimal. Yeah, this is the final solution. Then let's now to see the A star algorithm. The A star, it's the most popular informed search graph-based search graph-based algorithm. I'm sure of that. And it combines 2 things. If you remember, in the Dijkstra, the only thing that we rely on is on the cost of reaching a node. Okay? In the Dijkstra, we call it D of n. Here we call it G of n. This is, it's not a mistake from me. It's because if you check the textbooks, in Dijkstra they always put a D, and in A star they always put a G, and I've just respected that. Okay, but it's the same concept. The D that you see in Dijkstra, that is which is the cost to reaching this particular node. In A star, it's called G, and it's exactly the same concept. And then it has a second term, that is the heuristics. That is the only thing that we were using in the greedy, in the algorithm that we have just seen, this greedy search algorithm. Then A star, what it does is just combine these two elements in this function. And then for each vertex n, or for each node n, we combine the cost to reach the node plus this assumption or this estimation of reaching the goal. And just doing that, it's basically applying the Dijkstra algorithm, but considering these two elements instead of only the G. The heuristic has to be admissible, as we have said before, then it never estimates the true cost. It's efficient. It means that it can find the optimal path without exploring the whole graph, that this is what is interesting. Imagine the graph that Google Maps have. It's quite different than the graphs of 5 nodes that I show you here, okay? It has billions of nodes there. Then being able to find a path without exploring the whole graph, it's super important. If in this equation we say that the heuristic is 0, remember that an heuristic of 0, it never always estimates the goal, and it's an admissible heuristic. What it happens is that we obtain an algorithm that is almost equivalent to Dijkstra, if the heuristic is 0. And if we are unable to compute the cost for any reason, we assume that all edges have cost 0, for instance, that is positive. It's positive, it's not negative, at least. It's not negative, then we have the greedy algorithm that we have just seen, okay? Then it's what I told you, that the greedy algorithm is just in the middle between Dijkstra and A star. Here is the original paper. As you can see, it's not pretty new, but at least it's a little bit newer than the Dijkstra one. This is the step that we have to follow. Again, we are going to use the two queues or the two lists, the open or the two sets, if you prefer, the open set and the closed set. And initially in the open set, we'll have only the starting node, and in the closed set, we'll have nothing. The h function, again, is just a function that returns a real with estimated cost, tell it distance, energy, time, whatever you prefer, to reach the destination, to reach the goal. And then we have this f function that sometimes, or in some algorithms, is explicit. It means you can track it, you can record it, but in the end, if you record the g and you record the h, you don't have to store the f function anywhere. But because this queue or the set, open set, now the key of the open set, that when we need to select one node from the open set, what we are going to check is if is this fs. I recommend you to store that as a number, then it's a little bit easy when we do the algorithm. But the algorithm follows the same flow than the Dijkstra almost. We extract u from the open set, and we use as a key, instead of the one that has the minimal cost, the one that has the minimal f. We put it to C, but taking from here or removing, it's almost the same. If this is the goal, we are done. We just can reconstruct the graph using the pi function. And if not, for each neighbor of U, we compute its, for each neighbor of B that is not in the closed set. We don't have to do it for the neighbors that are already in the closed set. It makes no sense. Then, for each neighbor of B, what we do is we compute this tentative cost, that is the cost of reaching U plus, again, the W, the wedge of this edge, or the cost of this edge, as I told you. Sometimes it appears as C, sometimes it appears as W, sorry. And if this, okay, here we have it. If the B is not in the closed list, neither in the open list, no. Or it's not in the open list, or if it's in the open list, the t is smaller than its current g value, then we just said that for reaching B, we have to do it from U, and the new cost is t. Okay, the cost, the real cost of reaching this node. And because we have updated the cost, then we have to update again the F of the node B. H never changes because H is an estimation, is an heuristic, and it depends where we go. It depends on the goal, not how we reach this particular node. I don't care how I reach node B, the heuristic will be always the same, but because the function F depends on H, but also on G, and G here changes because the estimated cost of reaching G now has changed, then I need to update both of them. Okay, if at some moment, the idea of this algorithm is that at some moment we reach this point, okay, that the node that we extract from O, it's the goal. And here is where the algorithm should terminate. If at some moment this happens, that the set or the QO is empty, O becomes empty, it means that there is no path. There is no path to the goal. Here you can see exactly the same, but in an algorithmic way. I'm pretty sure that I updated some of these slides. I will upload that by the end of the class because I found some small mistakes and that I think they should not be here. Okay, just giving these heuristics. The heuristic function, the start node, and the goal node. We just update all the costs initially to infinite, except for the starting node that we set it to 0. We set all the policies to null because we don't know how to reach any node at the beginning. And then to the set O, that is this mine priority queue that we k with the function fb, that the function fb is gb plus hb, we insert s on it. That's all. And we keep the closed list as empty. And then we just extract the node u with the minimum f. If it's goal, we are done. We just remove it. Again, it's possible that here one of the neighbors is the goal. And then we update the goal. The moment in which we update the goal, we are not done. We are done the moment that we remove it. Sorry. Sorry, what is the?
WUV.
Where?
11 line.
Which line?
11.
11. Yeah, the W is what I told you. Sometimes I put it W, sometimes I just put the cost. It's the cost of from node U reaching the neighbor B. Is the age. Basically, W means the wage of the age. And in some, I think in some slides I put W and in some I put cost. It's just that. Okay, then if the node is what I was telling you, the function finalizes when the goal node is the one with the minimum f, not before. The moment in which you update the goal node for some other cost here is not the moment in which the algorithm finalizes. It finalizes when you check it here, when you extract the node u with the minimum f from the set or the QO, and it means, it results that this node is the goal, not before. This is a very common mistake. Whenever we have checked that the current node is not the goal, we just add this goal to the closed set. And then for all the neighbors of this node, we compute this tentative cost. And if the node is not already in the closed list, of course, in the implementation, you can do it a little bit different to avoid computing this cost if it's already in the closed list. Basically, yeah. If it's not in the open list or it's in the open list, but the wage, the G, the cost of reaching this node is bigger than the current cost. If it's equal, we don't change it, okay? But if it's smaller, basically to avoid operations. But if it's smaller, the tentative cost than the current cost, remember that at the beginning, the current cost for all the nodes is infinite, then we update it. Let's do a small example. Okay, here there are some drawings. Again, we initialize. Here we need not only the heuristics, but we also need the real cost, the W, from this node to this node, from this node to this node, from this node to this node. Okay, and here is how the algorithm evolves until, okay, evolves, until we found or we reach the last node. If you look here, there are several nodes that are still to infinite. Okay, not many in this particular case, but at least 1, 2, 3, 4, or 5 nodes that have not been expanded. It means that we don't need to explore all the nodes in order to see that this is the better path. In some situations, the advantage of using A star over using just a standard Dijkstra is not a lot. Okay, maybe we are improving at 20%, efficiency 15%, maximum, no more than that. Okay, in some other cases, yes, it's greater. Okay, just using the same setup that we had before, let's try to apply here the A star algorithm. As you see, I see. I put the Bs only in the A star and not in the greedy search. My fault. I thought it was all the slides. No, I only update this one. Okay, here what we have is the heuristic for each node. Okay, this is the heuristic for each node. For node B1, the heuristic, my assumption to reach the goal that is in here, it's 7.8 meters, kilometers, whatever energy, kilowatts of energy, seconds, whatever you decide is your cost. But I need also the cost for each specific edge, and I put it the cost here. Okay, I need the two things. Remember, in Dijkstra we only need these costs, the cost for each edge, and in the greedy search I only need the heuristics. Now I need both of them. How we compute that? Again, we create a table like the one you have seen before. Initially, B1 is the only one in the open list. Then I select the one that has the smaller Fn. The smaller Fn will be this one. Then I select this. And because B1 has 3 neighbors, B2, B3, and B4, I put B2, B3, and B4 in the open list. They will be all in the open list. The heuristic function, I just copy. For B2, what is B2? B2 heuristic function says 6. For B3, it says 5.8. And for B4, it says 5. But I need to put also the cost. And the cost, if you remember, I need to compute the tentative cost. Initially, for all of them, this cost will be infinite. But now I have to compute the tentative cost. The tentative cost of reaching B2 is the cost of reaching B1, that is 0, plus W. The W is this 5. Okay, W between B1 and B2, that is this 5.0 here. Then this will be no infinite, but 5. Then now I can compute Fn, and it's 11. For reaching B3, now the tentative cost is 0 plus 2.2, and here it's 6, 7, 8, no? And for reaching B4, the node 4, it's 0 plus 3.2, and then here it's 8.2. Okay. This is no longer in open list, now it's in the closed list. And the pattern of all these ones is B1, 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 and B1. Now I need to select, according to the algorithm, the node in the open list that has a smaller Fn. And here it's the B3. Then I select B3. B3 is here, okay, in the graph. And then for each neighbor of B3 that it's not in the closed list, then only B5, because B1 is already in the closed list, then B5. I add here B5. And I need to put the cost of reaching B5, okay? The cost of reaching B5, of course, again, initially it was infinite. Now I need to check if it's smaller or not. The cost of reaching B5 will be the cost of reaching B3, that was 2.2, plus 2.2 more, then it's 4.4. 4.4, no infinite, but 4.4. And the heuristics to reaching B5, for reaching the goal from B5 are 4.1, then my function is 8.5 here, 8.5. It's in the open list, and I've reached B5 from B3. Then I store here the parent, it's B3. Okay, let's continue. I've done another loop in my iSearch algorithm. I have to select from the, sorry,
B3 will be closed.
exactly, is what I was going to say. B3 is not any longer in the open list. Now I have 3 nodes in the open list, B2, B4, and B5, and I have to select the one with a smaller event, that is B4. Then let's check B4. We take B4, we remove it from the open list and put it in the closed list. And then for each neighbor of B4 that is not already closed, that basically are B6 and B7, B6 and B7, I need to compute its cost, assuming that I come from B4, okay? I come from B4. And I already know the heuristics. The heuristics of B6 is 7.6. And the heuristics of B7 are 5.0. I already know that because I only need to know the heuristic function, okay? Then the cost of reaching B6 from B4 is the cost of reaching B4, that is 3.2, plus 3. 3.2 plus 3 is 6.2. 6.2, and the cost of reaching 7, it's 3.2 plus 3.2, 6.4. 6.4, okay? I'm doing okay, yeah? If I do any mistake, you tell me. Now I have to compute event. Event is 8, no, it's 13.8. I don't write it very nice. 13.8, and here it's 11.4, no, 11.4. And both of them are in the open list. Okay, then I have B2, B5, B6, and B7, all of them in the open list. Let me check which one of them has a smaller Fn, and I think that is clear, that is B5. Okay, B5 is 8.5, while the other are 11, 11.4, or 13.8. Then let's choose B5. Where is B5? B5 is here. Okay, here on top. From B5, I need, I move that to the closed list. And I need to check which are the neighbors of B5 that are not already in the closed list. And basically, the neighbors of B5 that are not in the closed list is B8. It's only B8. Okay, how is the tentative cost? I say tentative cost because maybe I have a number here that is bigger than the current cost. This is what is tentative, okay? If it's bigger, I'm not going to update it. If it's smaller, I want to update it. Because right now, the cost in B8 is infinite, probably will be smaller. Okay, the cost, I will reach B8 from B5, we have said B5, and the cost of reaching B5 was 4.4, plus 4.1, that is the cost between B5 and B8. 4.4 plus 4.8 is 8.5. 8.5. Okay? Yeah. Then the heuristics from here is 0. I know it. It's 0.0 because this is the goal. And then I'm not done, okay? I'm just added here the goal, but doesn't mean that I have to compute the Fn, that Fn is 8.5. Said that this is in the open list, and it's in the open list. It's the moment in which I move this in the closed list, the algorithm will be done. And now I have to check which is the next node to check. In the open list, I still have B2, B6, B7, and B8. And now, yes, B8 is the one with a smaller Fn. Because this is the one in the smaller Fn, the moment in which I cross that and put this in the closed list, I can say, yeah, the algorithm is done. And then I can try to draw. Then from B8, the node I have to go to is to B5. Then from B8, I should go to B5. And from B5, I should go to B3. And from B3, I should go to B1. Then now, as different than in the other case, that in the greedy case, that in the greedy case, if you remember, we discover this route here. Now we have found a better route. A more efficient route is the optimal route for this particular graph. Okay? This is the kind of tables I will ask you to do in the exercises. I upload an exercise, now I will comment it. And this is mostly the algorithm, the A-star algorithm. Probably most of you already know it, but it's always good to refresh it because all these algorithms are super similar, and I need to be careful that I don't confuse something from one algorithm to the other because they are super similar. But for the Informat, well, not the Informat, but for the Dijkstra, the greedy one, and the A-star, it's very similar, okay? It's true that in the greedy and in the A-star, we use this open and closed list, while in the Dijkstra, we only use the queue, but in the end, you can implement it exactly the same way, okay? When we remove something from queue in Dijkstra, it's like if we put it in the closed list. And we only add elements to the queue. In the Dijkstra, sorry, we add all the elements in queue, and here we add the elements in node only one by one, only the neighbors. But if we add all of them all together, it will also work. The only problem is that we will have super large queue in the beginning, and in this way we keep it smaller. But it's more a matter of how you implement it than the main idea of the algorithm. The algorithm is almost the same. Okay, one just considers G, the other only considers H, and the other considers F, that is G plus H. It's just, this is the idea that I want you to take. Small comparison of all of them around the Uninformat or blind search, because you don't have anyone to guide you. DFS goes by levels and give us the shortest path if the graph is unweighted. DFS explores deeply and it's not optimal. It can reach, even in an unweighted graph, it's not optimal. However, uses less memory. And Dijkstra can expand the cumulated cost and create this graph that from any node in the graph, we can explain not only the cost, G or D. Remember that in the original, when I put you the algorithm, this was a D. Then not only expands this, but also computes the pi. Okay, all of them compute this pi function that tell us where I have to go from node whatever, to which node I have to go. And this is the path always inverse. Okay, the invert path. It's optimal for non-negative edged wedge, for non-negative wedge in the edges. And then regarding the Informat path, we have the greedy best first search that, as you have seen, is super fast, super easy to implement, but it's not optimal. And the other is the A-star, that basically is a combination of the greedy best first and the Dijkstra. And it uses this F function, that is the combination of the cost and the heuristic. And if the heuristic is admissible, is optimal. It will always find the optimal path. Things that you have to learn here to implement these 5 algorithms by hand, to implement them by code, to implement them in Python, to see if an heuristic is admissible or not, to implement your own heuristics, etc. There is just a last thing that I want to show you because it's related to what you will have to do in your lab. That is what happens if you don't have an explicit roadmap. I ask you to implement A-star, for instance, or Dijkstra. Well, Dijkstra will be maybe a little bit more challenging, but A-star, and your environment is not a graph in which you have connections between your nodes, is a grid map. Okay? Can we still apply a graph search algorithm if our environment is discretized, is a kind of map with cells? Yes, we can do it. The first thing that we need to do is to know which are our robot motions. For instance, we can assume that we can move forward, right, left, backwards, or we can just move in diagonal, things like that. And then for the graph expansion, we are going to create the graph, to create the roadmap, basically when we need to access the roadmap, when we need to check the neighbors of a particular node. No, we are in this node, and we need to check which are the neighbors of this particular node. Instead of going to the graph and asking this question, tell me all the neighbors for this particular node, what we are going to do is, using the robot motions, we are going to expand. From this position, I can reach this, or this configurations, nodes, whatever you want to call it, according to the available motions that I have. And what we need to see is this motion possible in this particular state? Imagine that you are in this position, you can move forward, backward, left, or right, but it results that here there is a wall. Then, of course, you cannot move right. Then you need to do this validity check and see, okay, from this position, I can expand my graph, or I can visit these 3 neighbors. Then, whenever you need to select the neighbors, you will select these 3 points, but not the one in the right, because it's not available. And then this is what we are going to do. No, we can apply a discrete version of the A star using, for instance, connectivity 4, assuming that in a grid you can move to the cell on top of you, below you, left or right. As a heuristic function, we just can use or the Manhattan distance, the Manhattan distance, in which you just count the distance in X, the distance in Y, and you add the 2 distances, or the heuristic function. You can use also the heuristic function. And when you do the node expansion, for all available motions, connectivity 4 or connectivity 8, you check if the cells are correct, are available or not, or you are moving on top of an obstacle or not. If you just do that, you can expand the graph on real time, let's say, while you are exploring, where you are trying to do it. Imagine in this situation, okay, we start here, we want to reach here, and we can move left, right, up and down. Then what we are going to do, first, we expand. We say that we can visit these 4 positions here, and then we expand our graph. For each one of these positions, I can expand it again. Sorry, it's not very clear, but this cell, all these cells now are in light green. If you check in your laptops, maybe you will see it perfectly. It means that now from these cells, we can reach or maybe the same cells, or maybe from one cell we can go to another, etc. It's a graph, okay? There is a lot of interconnections, etc., etc., etc. Of course, when we are here, we cannot move, we cannot turn right, and when we are here, we cannot turn up, or here we cannot go up because it's the end of the wall, not for us. But we can expand this graph and finally implement the algorithm. This is exactly the same A star algorithm that I showed you before. The only thing that is, instead of for all neighbors of U, for all neighbors B of U, we say for each motion M, for each possible motion, up, down, left, right, imagine, check, compute the neighbor, that is basically from the current position, apply the motion, and if B is valid, then I do it. We have replaced it for all U of B for these 3 lines here. That's all, okay? For the rest, it's exactly the same algorithm. It's only this is the new part. Then this is what you will have to do in the labs, basically, implement an A star. I think the 2 versions of them, if I remember well, one, we will give you a roadmap, graph codified in a text file, and in the other, we will just give you a bitmap, and from this bitmap, you will need to explore using connectivity 4 or connectivity 8. And that's all. And just what I wanted to show you, that I told you before, here is when we move from this original position, the green point, to the final position, no, to the red point. This is the best, the optimal path that you have to follow. Here, we have used this discrete version of the A star. And what is nice of this discrete version is that it's very simple to plot which are the nodes that you have really expanded. And I plot here in green the path, and in yellow, the node that has really explored, that has been added to the O set, okay, the open set. You can see that here, for instance, is quite efficient. In the first one, we have explored maybe 40%, 50% of all the nodes. However, in the second one, is not so efficient, neither in the third one, okay? It's what I told you, the benefits of using A star, although we have a very nice heuristics, for so low dimensionality for a two dimensions problem are not huge. If you consider the extra effort that you have to do for each step, then you do less steps, but each step is a little bit more costly. Of course, when we grow, when our dimensionality grows, the benefits also grow.